This video is presented to you by www.testprepadda.com. Dear students, in this session of electrochemistry, I will talk about Kohlrausch's law and its application. First of all, what is Kohlrausch's law? You can see here the law says at infinite dilution, when the dissociation of electrolyte is complete. Let me tell you again the meaning of this infinite dilution. Infinite dilution does not mean that we have added infinite liters of water. Infinite dilution means that stage of dilution after which no significant change in molar conductance on further dilution. My point is clear. So, at infinite dilution, when the dissociation of electron is complete, each ion makes a definite contribution towards the molar conductance of the electrolyte, irrespective of nature of other ion with which it is associated, and that the molar conductance at infinite dilution for any electrolyte is given by sum of the contributions of the ions. Now if I say NaCl electrolytic solution, and this solution is infinitely diluted. According to the law, if you find molar conductance of NaCl at infinite dilution, it will be summation of molar conductance of Na plus at infinite dilution and Cl minus at infinite dilution. And another interesting point here is that the contribution of Na plus is not influenced by Cl minus, by the presence of other ion. Whether Na plus is present with Cl minus or Br minus or any other anion, the contribution of Na plus will remain same at infinite dilution. This is Kohlrausch's law. For acetic acidiferrite, molar conductance at infinite dilution, it will be molar conductance at infinite dilution for CH3CO minus plus molar conductance at infinite dilution for H plus. If I write molar conductance at infinite dilution for CH3CONA, I will write this as CH3CO minus plus Na plus. Now the contribution of Na plus here and contribution of Na plus here, magnitude wise both will be same, and the contribution will not be influenced by the presence of other ion like Cl minus or CH3CO minus. This is the Kohlrausch's law. Now I will talk about the application part. First application is to determine the molar conductance at infinite dilution for a weak electrolyte. Dear students, if you recall session number 4 of this electrochemistry, there I told you the graph between lambda m and root c. For strong electrolyte, I gave the graph like this, and for weak electrolyte, I gave the graph like this. And there we have concluded that for strong electrolyte, the value of molar conductance at zero concentration or infinite dilution can be found directly from the graph by extrapolating this. But for weak electrolyte, it cannot be found. Molar conductance at infinite dilution for weak electrolyte cannot be found directly from the graph because the graph becomes parallel to y-axis as concentration tends to 0. So we will use indirect method, and that is Kohlrausch's law. Consider CH3COOH. This is a weak electrolyte. If I use Kohlrausch's law, I will write this as lambda infinity CH3COH is equal to molar conductance of CH3CO minus at infinite dilution plus molar conductance of H plus at infinite dilution. Because we know it does not matter whether H plus is present with CH3CO minus or some other ion. I will take the help of that point. I will add Na plus here. But at the same time, I have to subtract this ion. So minus lambda infinity of Na plus. Now H plus. With H plus, if I put Cl minus, I have to subtract that Cl minus. Now, as we said that for weak electrolyte it cannot be found. Now, if I combine CH3CO minus and Na plus, it is a salt, and salt is considered to be a strong electrolyte. CH3CONa plus. If I combine H plus and Cl minus, it will become HCl, which is again a strong electrolyte. Now, if I combine Na plus and Cl minus, it will become NaCl. Again, it's a strong electrolyte. So, this is a strong electrolyte. This value can be found directly from the graph. HCl is strong electrolyte. Molar conductance at infinite dilution can be found directly from the graph. This NaCl is a strong electrolyte. So, molar conductance at infinite dilution can be found directly from the graph. This we can find directly, this we can find directly, this we can find directly from the graph. So, indirectly we get the value of molar conductance at infinite dilution for CH3COH. That is a weak electrolyte. So, this way we find the molar conductance at infinite dilution for weak electrolyte. Now, to understand this in a better manner, I will take a question here. Here the question says, the molar conductances of sodium acetate, hydrochloric acid and sodium chloride at infinite dilution are 91 into 10 raised to minus 4 ohm inverse meter square mole inverse and 426.16 into 10 raised to minus 4 and 126 into 10 raised to minus 4 ohm inverse meter square mole inverse respectively at 298 Kelvin. What is the molar conductance at infinite dilution for acetic acid? For acetic acid, which is a weak electrolyte, we have to find molar conductance at infinite dilution. If I use Kohlrausch's law, I can write as CH3CO minus plus H plus. Now look at the values given. Sodium acetate, hydrochloric acid and sodium chloride. So what are the other ions except CH3CO minus and H plus? Na plus and Cl minus. So we have to use these two ions to convert this weak electrolyte into strong electrolytes. So here I will add Na plus, here I will add Cl minus, and then we have to subtract Na plus and Cl minus. This combination will become CH3CONa, sodium acetate, whose molar conductance at infinite dilution is given. Then another combination is HCl, which is also given, minus another combination is NaCl. Now substitute the values here. For CH3CONa it is given as 91 into 10 raised to minus 4. For HCl the value is given as 426.16 into 10 raised to minus 4, and for NaCl the value is given as 126 into 10 raised to minus 4. And if you solve, the value comes as 391.16 into 10 raised to minus 4 ohm inverse meter square mole inverse. So this is the molar conductance at infinite dilution for CH3COH. Dear students, just have a look at molar conductance values of some common ions at infinite dilution in aqueous medium at 298 Kelvin. These are some common cations and these are some common anions. You can see for H plus the value is very large, 349.83, and the high value of molar conductance at infinite dilution I have already explained in session number 5 of electrochemistry with the help of Groth's mechanism. Just have a look at these values. Now I will talk about another application of Kohlrausch's law. This is the second application to determine the degree of dissociation and dissociation constant of weak electrolyte. Recall the session number 4. There I told you that for weak electrolyte we can write degree of dissociation alpha as lambda m upon lambda m at infinite dilution. This lambda infinity we have just found in the application number 1. Once alpha is found, you can get the dissociation constant by writing the dissociation equation of the electrolyte. For example, if I write CH3COH giving CH3CO minus plus H plus. If I write initial concentration as C here 0 0 and at equilibrium C minus C alpha here C alpha C alpha. So dissociation constant, that is equilibrium constant, can be written as product concentration upon reactant concentration, and if I substitute C alpha into C alpha upon C minus C alpha, I get K as C alpha square upon 1 minus alpha. Now here alpha is found, alpha you substitute here, and this way we'll get the value of K, dissociation constant of weak electrolyte. Now to understand this concept, I will take one question here. Here the question says the molar conductance of 0.01 m solution of acetic acid was found to be 16.3 into 10 raised to minus 4 ohm inverse meter square mole inverse at 298 Kelvin. So lambda m is given as 16.3 into 10 raised to minus 4 ohm inverse meter square mole inverse. Now, the ionic conductances of hydrogen and acetate ions at infinite dilution are this and this. So, if I use Kohlrausch's law, I can get lambda molar conductance at infinite dilution for CH3COH, because law says it is the sum of molar conductance at infinite dilution of ions. So if I substitute here 349.8 into 10 raised to minus 4 plus 40.9 into 10 raised to minus 4, the value comes as 390.7 into 10 raised to minus 4. Now, question says find degree of dissociation and dissociation constant of acetic acid. Degree of dissociation we know lambda m upon lambda m at infinite dilution. If I substitute value 16.3 into 10 raised to minus 4 upon 390.7 into 10 raised to minus 4, this value comes as 0.0417. This is the degree of dissociation of acetic acid. And for acetic acid, if I want to find a dissociation constant, I will use Ka is equal to C alpha square upon 1 minus alpha. But you cannot use this expression every time. You have to write the equation of dissociation for the given compound. So here if I substitute, concentration is given as 0.01 into 0.0417 whole square upon 1 minus 0.0417. If you want, you can neglect this with respect to 1. And if you solve this, the value comes as 1.814 into 10 raised to minus 5. This is the dissociation constant of acetic acid. My point is clear. Dear students, in the next video lecture, I will talk about some more applications of Kohlrausch's law. Thank you. This video is presented to you by www.testprepadda.com. testprepadda.com provides free audio-visual lectures of different subjects by expert faculties, free online tests prepared by expert faculties to students who are preparing for engineering or medical entrance exams or planning to take exams like KVPY, Olympiad, etc. It provides a platform where students can interact with mentors to improve their performance in the exams. The mission of this online medium is to help students to achieve their goals. Log on to www.testprepadda.com to watch free video lectures on different topics, to download free revision notes, to take free chapter-wise online tests, progressive test, and mock test, to discuss doubts with mentors. Thank you for watching the video. To stay up to date with the latest videos, subscribe to our YouTube channel. Like us on our Facebook page, Test Prep Adda. All the best.